you liked the demo. Now I'm going to talk about how the renderer works. There's a lot of stuff going on, and this is basically your graphics 101 squeezed into 5 minutes. So make sure to pause every slide and try to understand. Now let's get started. First, let's talk about rendering pipeline. The first step of rendering is to load the object to memory. Wavefront file is a simple format that uses text to define a 3D shape. Here is an object file for a cube. The program locates the faces and find each vertex. A polygon is then formed. Then the polygon is divided into triangles. Here's what the loaded object looks like in memory. Then we need to project the 3D file onto screen. We just need to delete the depth information in theory. But there is a problem. Since the screen is pixelated in a different coordinate system, we need extra code to translate between the two coordinate systems. After the 3D mesh becomes a flat 2D soup, we can proc to draw it on the screen. Given 2 point, we can draw a line, easy. And connecting 3 points with lines, we got us a wireframe triangle. Filling the triangles takes longer. We need to divide the shape into 2 and fill the top and bottom section separately. So here the top section is filled. Though we proceed to the bottom section, we got our nice filled triangle. Here's what it looks like when we combine the 3 steps. The cube is indeed projected, but we can only see one of the faces since the others are overlapped and it does not look very 3D. To address this problem, we need to understand the human vision. See, there's a common phenomenon where object that is further away appears smaller. This phenomenon is called perspective. And it's well understood by artists to make 2D painting looks 3D. See how everything in the painting converges to a point behind Jesus. Here are some concepts, pause and read it yourselves. Homogeneous coordinates is basically adding one dimension to allow us doing more transformations that are not possible by 3x3 matrix. Translation is one example. Here's the perspective projection matrix. I can't really go into details about it. For now you can just think about it as a magical black box. 3D shape goes into it and comes out projected. Here's some follow-up operations. Now after the transformation, we can see the cube start to look like a 3D object, and the far end does appear smaller, which is exactly what we want. Now we talk about functions that transforms the mesh. The first one is translation and can be done by NumPy addition. For rotation, we use 3 rotation matrix to rotate the object on 3 axes. We can also use an enlarge matrix to resize the object, but again, we can use NumPy to accomplish this in one line. So we zoom out, which is translation on z-axis, the object a little bit and rotate it on x and y-axis. This looks great. Illumination basically exploits the dot product to calculate the difference between face direction and light direction. If light is parallel to the normal, perpendicular to the plane is 100% illuminated. If the light is perpendicular to the normal, the plane is only half lit. Now every face of cube is properly illuminated. Because nobody wants to sponsor me a NVIDIA graphics card, I use CPU render, which is slow. How can we improve the performance? So first, a profiler is used to track the bottleneck. Sort by come time, and we can see rotate vector function is really high on the list. By the way, this is an odd choice of name. Here's the original code. Here's the improved version. We did all the trig calculation beforehand to avoid repetition and combine the 3 matrices into one rotation underscore matrix. And looks like we saved about 1/3 of the time. This is how to optimize. Normal clip uses same technique as illumination, only the light comes from camera this time. Basically anything not facing camera gets clipped. Now this looks close to perfect. Drawing triangles takes a lot of time, so we want to avoid if possible. So Z-buffering makes the program choose to not draw triangle if there's already something on top of it. If triangles are close to the screen, they become large and can take quite some resource to draw. We can clip the triangle edges and form new polygons. Like that. Clipped shapes can also form a pentagon, or more. Now up until this stage, the rendering pipeline is really complete, and that's basically how 3D Engine works. All the key lines of code has been given. Try write you own. At the end, we can also use multiple processes to render different frames and combine them when it's done. We use joblib for the task. Here's the comparison between not using multiprocessing and using it. The rendering speed is boosted 3 times. I bought the whole CPU, so I'm gonna use the whole CPU. I concluded some steps for optimizing NumPy and Python programs in general. Here's some other NumPy specific suggestions. I also found an article written by past Alberta students discussing polygon reduction, which is the process to reduce face count to boost performance. I plan to implement the feature in the future. All the illustrations in the PPT are drawn by myself using Inkscape. And that's it. Thanks for watching, guys.